I am Graham. I'm the Keeper of Geology at Dudley. I'm the chairman of the society, for those of you that don't know me. And Keith isn't able to make it tonight, so I'm afraid you're going to have to put up with me. I'm undoubtedly not going to do such a professional job as Keith, because he is exceptional as meeting secretary and host. So let me introduce you to Dan. Dan is currently researcher at Warwick University, data analysis with the university, but he cut his teeth on geology as a black country lad from Walsall, and then went on via Birmingham University to study paleobiology. He then got sucked into by Professor Richard Butler into the vertebrate side of things, so studying tetrapods, mainly dinosaurs, he tells us. And now he is, as you've heard, continuing some research, but also working on things like the Birmingham Boulders project. So without further ado, Dan, I'll hand over to you.
Yeah, thanks, Graham. Thank you so much for, well, firstly, just for that introduction and for inviting me to give the talk. It's a real privilege to be here. Well, to be giving the talk to you. Unfortunately, it's not in person. And it's great that I'm doing this for the Christmas talk. It's really nice to be here. And my talk is called the Deciphering the Fossil Record, Preservation, Practice and the People. And it's barriers to understanding the evolutionary patterns in the fossil record. And this is largely based around the work I did for my PhD. Oh, I just had an introduction, but I left a slide in there. But basically, my PhD was entitled "The Completeness of the Dinosaur Fossil Record and Disentangling Geological and Anthropological Biases." I mean, just for anybody who doesn't really know, doesn't really know what a PhD actually involves, because I sure as hell didn't when I started. A PhD is essentially just 3 or 4, maybe more if you're keen, research projects and dissertations and under one like umbrella subject, and that combines to form like your thesis. And it's wonderful, it's fun, and it's insanely stressful at exactly the same time. And the product of that research is essentially these 3 papers. The first was looking at the theropod fossil record, the second looking at a revisitation of the sauropod fossil record, and the third was looking at the potential identification bias in theropod dinosaur fossil record. And that's what the bulk of tonight's talk is going to be about. I mean, for my research, I was essentially interested in understanding true large-scale patterns in the fossil record. And what I mean by that is like the changes in diversity and distribution of species at different times in geological history, and also changes in other things like morphological diversity, like changes in body size, for example. And so like in these examples that are on the screen, time is going from like left to right, and it's getting younger on the right. And changes in the patterns of diversity for all vertebrates is on the top left, and for dinosaurs in the bottom right. And so this is the kind of thing I was interested in understanding, essentially trying to understand the overarching story of life on Earth, but specifically sort of for dinosaurs. However, there are things that can skew our interpretations of this, and since mainly since the 60s and 70s, paleontologists have noticed that like these face value patterns that we can take from the fossil record, like this big data we can take from the fossil record, can actually be is actually like closely followed by the number of geological formations and other geographical and sampling artifacts. So essentially, some of the patterns that we're seeing are reflecting the geological record and not solely biological and evolutionary signals. And so really we have to get over this problem and try and get to some of those evolutionary signals. We need to understand some of the issues or the barriers that are in our way. And there are a number of potential biases in the fossil record. And firstly, there's variable distribution in the geological outcrops. When you find fossils, there's variable preservation levels. And the effort to extract those fossils is also variable depending where it is, what it is, when it is. And when we find fossils, interpretations can also differ. Like individuals can disagree and people can just get things wrong. And this then, filters into what we consider useful taxonomic and phylogenetic information, and this informs our evolutionary understanding. So for my research, I was essentially interested in all sort of these stages. But I was mostly concerned with using the data stored in scientific literature to help understand biases in the fossil record. And this bore out from some previous research that was done about 10 years ago, well, and maybe a little bit further back than that. And there have been various methods devised attempting to decipher true evolutionary patterns in the fossil record. And some of these I will touch on in the talk. But for me, I was trying to quantify the completeness of the fossil record and try to prize out particular issues that could get in the way of our interpretations. So the two main words you take from that are dinosaurs and completeness. And for the first thing is, what actually are dinosaurs? I think it's important that I define that when I'm talking about them. So on the left is a simplified tree of life showing how different vertebrate animal groups relate to each other via these different branches. You can see that humans are, the little human figure is represented in the mammal section, and we have a common ancestor with a reptile group at node number 4. And dinosaurs would fit somewhere on the lineage leading to the chicken, after node number 5. And they are essentially terrestrial archosaurs, which are a particular group of reptiles, and they share common ancestors with crocodiles and are closely related to pterosaurs, and pterosaurs are not dinosaurs, which is commonly confused. And within Dinosauria, there are 3 main groups. There's the Ornithischia, a diverse group of herbivorous dinosaurs, and mainly lineages which have the striking body armor and decorations, like the species like Triceratops and Stegosaurus. There's Sauropodomorpha, which are the herbivorous long-necked dinosaurs like Brontosaurus and Brachiosaurus, and there's Theropoda, which is the mostly predatory dinosaurs like Tyrannosaurus rex and Velociraptor. And this group is where birds, evolve from. And for my PhD, I only looked at sauropodomorphs and theropods, and both these evolved in the late Triassic and went extinct at the end of Cretaceous 66 million years ago. And importantly, I looked at non-avian theropods, so no birds, and exclusively looked at like the body fossil record, not looking at tracks or anything else like that. And the next thing I should explain is what completeness is and what I mean by a complete fossil record. I mean, again, there's been various methods that have been used to quantify completeness of the fossil record, like figuring out how many gaps there are in a geological record or in a stratigraphic column. But for my research, completeness was how much of a skeleton or how much phylogenetic information is known for each individual species. And this method was devised in 2010, and it's really useful actually to compare to stuff like diversity patterns or abundance patterns, because it really gets at like the heart of the taphonomy of the actual fossil itself. And the image on the right shows the relationships of some abelosaurid theropod dinosaurs and the associated skeletal material known for each species. And we can see that each species has been recognized by variable skeletal material. Like Majungasaurus is known from a complete skeleton, and Abelisaurus is known from just like a skull. And I'm not going to go into the details, but basically for my data collection, I would figure out what proportion of a full skeleton is preserved for each individual specimen of each species, based on like some skeletal body proportions, which are represented by that Allosaurus skeleton there. And I would combine these species completeness scores, and I would use that to quantify the completeness of like whole groups. And specimen completeness has been shown to be like strongly affect our interpretations of just individual species. So, for example, in 1965, a species of theropod dinosaur called Dinosaurus was found and named based on these pair of isolated and large and pretty fearsome-looking forelimbs. And at the time, there was a paper postulating it might have been like a super predator, although it did have features that was a bit like an ornithomimosaur, like Gallimimus from Jurassic Park. But it largely remained a mystery until 2014, a paper was published showing that with a lot more additional material from the same locality with matching arms and stuff, and we found out that it was actually much weirder than we expected. It was a humpback, like duck-faced ornithomimosaur with these giant claws, and in some ways it was actually mimicking, well, maybe not mimicking, but it had parallel evolution with another group of theropod dinosaurs called Therizinosaurs. And also another example of this sort of thing is a very recent discovery of like this really complete Spinosaurus tail, which has sort of changed our interpretation of this animal again, which there's been many iterations of it. And it's now thought to have been even more crocodilian in appearance and ecology. And it's got this, possibly this tail-propelled, locomotion. So there's good reason to sort of understand the influence of specimen completeness on these large-scale patterns in dinosaur fossil record. But my research was like highly quantitative and was largely involved like shifting through the paleontology literature and scoring every specimen of theropods and sauropods, and then doing this doing multiple levels of statistical analysis. And like I scored like 8,000 specimens. It might be more than that actually. I'm not too sure. And like 1,000 species. And like this picture of my friend Andy Jones pretty much demonstrates how that data collection made me feel at times. And for this talk, I don't really want to go too deeply into that. So to avoid boring you to death with some of that stuff, and maybe awaken some like sort of my personal Microsoft Excel nightmares, I'm gonna sort of walk you through some of my fieldwork experiences that I was fortunate to have during my PhD, and hopefully showcase some of those barriers that I previously mentioned, and some of the things that are actually amazing about the fossil record, but whilst also explaining some of the main results of my research in a more natural way than just sort of blurting stats at you. It might not work, but let's see. So yeah, I was very fortunate. I was very privileged to be able to go on 2 paleontological expeditions to South Africa in 2017 and 2018 in association with the University of Witwatersrand. We were there on initially we were there on trips to prospect and excavate in the famous Karoo Basin, which preserves sedimentary deposits which span like 100 million years, like from the Carboniferous to the Jurassic. And the Karoo is incredible. It covers like 2/3 of the country's land surface, and it's just ridiculous. And for me, it's most famous for like the quality and diversity of terrestrial vertebrates that have been found there. Things like modern amphibian ancestors, phytosaurs, which are like convergent to have parallel evolution with crocodiles. They're not crocodiles. Other archosauriforms, like these predatory erythrosuchers, which had abnormally giant heads. Early dinosaurs, weird parareptiles, mammalian ancestors, anodonts like Lundstrager, which was like this amazing survival taxon after the end Permian mass extinction, saber-toothed gorgonopsids and cynodonts. So incredible diversity of finds has been found now. And when I first went in late 2017, we were prospecting for like new fossiliferous sites in the hope of finding new archosaur material. But we were looking in the Middle Triassic Bergersdorf Formation, specifically the Cynognathus subzone C, which was actually, I think you can just about see on that stratigraphic column. This member like notoriously sort of yielded scrappy material in comparison to oh, my computer is trying to set up something. That was weird. Jesus, what is it doing? I am so sorry about that. My Lenovo computer is trying to set up some weird thing, and that just keeps flashing up. Anyway, this member was notoriously yielding scrappy material in comparison to the other formations, other members in the Karoo. And we were going there to try and maybe improve that. But we flew to Johannesburg, and we took a 10-hour drive to this remote location in the Sturkstrom district of the Eastern Cape province, and you can see from that satellite image that there's basically nothing there. And we stayed in a remote hunting lodge, and it was pretty fun. We spent most of the day. We were fossil hunting, through the day on this huge game farm, and at night we ate had amazing barbecues, and we enjoyed the beautiful South African country, and generally the best skies I've ever seen. It was just crazy at night. And there on the right, that is the leader of the exhibition. That is Professor Jonah Chouanière from WITS. And he's there with a large, some important supplies. That's for our nighttime entertainment, and it was generally just an amazing experience and incredible amounts of fun. But South Africa, and in the Karoo, is absolutely perfect for fossil collecting, and this is because it's got a fantastic combination of lots of area and climate. There's vast area of accessible outcrop, and it's quite arid, so there's like almost very little vegetation cover to go. And then occasionally there's a lot of sediment disturbance because of big storms. So it's aided by its position on the planet. Basically, it's situated like in the mid-latitudes, and that's similar to some other famous and sort of bountiful localities in like the northern hemisphere, like Mongolia and China and North America and Canada. And so like it's true that modern climate and outcrop availability do sort of impact the abundance of finds that we get in the fossil record. And we can see this actually from the dinosaur fossil record if we look at the global data of the dinosaur fossil record. So here is a distribution of each theropod and sauropodomorph species occurrence. This is plotted with specimen completeness on the x-axis and the geographical latitude on the y-axis. The plot on the right of each dinosaur group, so plot on the right, so B, and on the right side of the sauropodomorph section, that's actually plots paleolatitude. So that's what the occurrence would have been during the Mesozoic, like where that would plot on the planet. And there's different colours there's different colours and things between the two plots because they're from two different papers. But what we can see is that there are occurrence peaks in both the northern and southern mid latitudes, and this falls away at the high and low latitudes. So in the tropics there are very few fossil finds, and so this generally reflects sort of vegetation cover on climate. There's way more occurrences in the northern latitudes, and generally seems that potentially there's more complete specimens in the northern latitudes. And these patterns are reflected in for all four-limb vertebrates. So on the right, this is the proportion of occurrences for all Mesozoic tetrapods in comparison to the sauropodomorphs. And then you can also see there's peaks in the mid-latitudes. There's potentially, within this, there's potentially some true evolutionary patterns affecting this distribution, but actually seriously striking just how large that modern northern occurrence spike is, which I think you can see here. And what this means is there's quite a divide between the fossil record northern and southern hemisphere. And another thing that drives these geographical patterns is actually sort of economics and the historical sampling efforts that's got into it. And traditionally, countries with the power to fund paleontology research, like the UK, Germany, the US, and China, have mostly sampled in like their domestic sites, at least originally, and they go back to sites they have easy access to, and they go back to sites that they know is going to produce good fossil material, and so that enhances some of the signals that we're seeing, and influences signals we're seeing. And even our trip, to South Africa, we were exploring sort of a poorly sampled geological unit, but we knew there was something there, and we knew we were going there because there was going to be fossils there. And this sort of generalized sort of sampling behaviour really has the potential to sort of distort the patterns we see in the fossil record of biodiversity changes through time. And this and the climatic regimes means there's actually strong differences between the fossil record in different countries and continents. So on the left here, there are two figures that are comparing and contrasting the completeness of the theropod fossil record and a sauropod fossil record per continent. And each of those grey boxes, so you might see a lot of these in the next coming slides, but these grey boxes are called Vial Plots, and Vial Plots are basically just box plots with an illustrative wiggle around them that represents like the abundance at particular values. So for each continent here, we are illustrating the range of species completeness scores, and you'll notice that most of them are quite bottom heavy and generally form a sort of triangular shape because most dinosaur species are known from lower skeletal completeness. For ease of comparison, the white circles are the median, or like the average value. And we can see that theropods from Asia and sauropodomorphs from North America have consistently high completeness levels. And here in this sort of Mesozoic geological, so here there is like a, so here's like a Mesozoic geological timeline represented along the bottom, going from the late Cretaceous to late Triassic to the young Cretaceous. And above it are the changes in species number, and the average specimen completeness is separated per continent. So we can see that because of these continental differences, there's actually, there's incredibly variable species number and completeness levels between different continents, and we get different peaks and troughs at different time bins, and so the global record is actually, is taken for, is like a large sort of interpretation from all these sort of regional signals, and they're quite inconsistent, and they're actually incongruent with each other. So these sort of regional geographical signals are actually playing into what we interpret on a larger scale. Yeah. So generally in global terms, like it's generally known that younger rock units have a wider spatial extent, so therefore they produce more fossil occurrences. And at face value, this tends to produce sort of patterns suggesting there's been this like exponential increase in terrestrial land vertebrates through time. And we generally believe that's not true. And in 2020, a number of colleagues of mine who are at Birmingham and elsewhere, they published a paper that looked at the impact of spatial sampling on diversity changes through changes for terrestrial four-limbed vertebrates through geological time, so tetrapods through time. And they found that not only was there the spatial distribution of fossil occurrences was strongly biased, but also the actual sampling efforts that was actually had a huge impact on sort of those face value signals we see through geological time. And when they accounted for those spatial biases, they actually saw that there's actually no great change in overall biodiversity in the last 100 million years, apart from a rise after the end Cretaceous extinction. So basically, it's very important where we decide to look and how we look for fossils, and it has ramifications later on when we're actually interpreting this information. And while I was in South Africa, it really struck home just how sort of basic some of our methods are for searching fossils. At the time, we were, there were occasions where we're driving along and sticking our heads out the car and like potentially, just pointing and going, oh, that looks like a good outcrop. Let's go over there and see if we can find some fossils. And that's fine. I mean, it was a tried and trusted method, and people making those decisions of where to go were highly trained, and it largely worked. But it's amazing to think as how much of some of the discoveries are just done by chance, and I think it just occurred to me because we really weren't finding too much. We were finding mostly scrappy bits of indeterminate bone, occasionally some recognizable bits of Dicynodon or Temnospondyl amphibian, and we were getting a bit despondent. And I just want to play, if I can play a little video for you. Let me just. I'm going to play this little video where me and my colleague Pedro Goddard, I think we're kind of losing it a little bit. I hope you can hear it.
And this is the normal thing we get here.
Yeah, it's a new dinosaur, isn't it, Pedro?
This is it's going to be called Creposaurus.
I agree. That's beautiful. It's beautiful stuff.
Yeah.
Best find of today, that.
Yeah, it was. For sure,
is.
Yeah. It's going to go into nature. Maybe science.
So the areas that we're operating are actually very well researched. So it was just huge that it was hard to like pinpoint exact places to look for fossils. But yeah, there's Pedro thinking that being a bit despondent. Oh, not to do that again. But there are methods that have been developed in the last 20 years to help speed up this process and sort of slicken paleontological discovery. and studies, quite a few have been, have been looking at, actually mostly looking at the hominin and primate fossil record, have used like remote sensing to map the topography, vegetation cover, land cover, like slopes and the drainage density and stuff like this. And they use that and they combine it into some sort of, and use some sort of preset criteria to predict like the fossil bearing localities. And this is just one example that was done actually for the Elliott Formation of the Karoo. And what happens is that people go out and verify these finds after they've predicted these places. So these things are out there to actually help make and process and make the the paleontological process more efficient, but probably less fun, I guess. But I also saw that this year there was a paper come out about using similar techniques to actually like predict like trace fossil sites on Mars as an attempt to maybe there's indications of past life there, which was actually kind of incredible. I mean, and they did apparently identify sites that could potentially have bioturbation, like there's evidence of life. But I imagine they have less chance of verifying those things, and it was a bit trickier than verifying it in the Karoo. But even finding very little, we weren't really despondent. We were having an amazing time. We were in an incredible landscape looking for fossils, and also we're in the wild, and because we were actually doing a lot of these fossil hunts in our game farm, we saw some incredible wildlife, including zebra, baboons. I mean, that was incredible. Like, these baboons were like screaming at us from the cliff top, and they like responded to us when we would make noise. There was tortoises and that secretary bird. That was incredible. But the most impressive for me was these giraffes. That was insane to see giraffes in the wild. We were just driving past, and then we saw this herd, and we got out the car, and then just like had this sort of standoff with them, and that was just ridiculous. Apparently, we were told that the giraffes weren't allowed to be shot on the game farm, which was good. Not sure how much I believe them, but I hope it's true. Also, one morning we also we just took a quick trip, and we were taken to see this rock art as well, and that's incredible. Yeah, there's a guy showed us, suggested that they weren't too old, they're maybe like hundreds of years old, maybe not thousands, but it's just insane. Like, this stuff was just completely untouched. There's nothing near it. You just walk up to it, and it's like, oh, there's some incredible rock art there. On the right there, you can see that there's just this like sort of humanoid figures. I hope you can make out. And there's one that's like there's little hands, this like cupped hands, and just that was kind of incredible. There's another thing that was sort of taking me back on this trip. There was so many things to see, and it was insane. But after about 5 days of prospecting in the Middle Triassic beds and finding scraps of bits of fossil, we decided to try and go out and look at some of the sites exposed in sort of the Elliott Formation, which is late Triassic and lower Jurassic in age. So it's a bit older, a bit younger, sorry. And it's incredible how different the preservation was. The contrast was quite incredible. So you can see that picture on the right. We parked up on the side of the road. We literally walked on the other side, and then I was just walking behind Professor Chouanier, and I just saw him like casually just like shift something spit something out of the sediment embankment, and it was like this entire skull of this Dicynodon, which is a non-mammalian therapsid, or it's a mammalian ancestor. But the difference in preservation in sediments that were largely sort of similar was really quite interesting. And it's important because it shows just how our understanding of species changes can be totally controlled by the geology. Like some of these diagrams show that I sort of showed a little bit earlier. I must also say that I was doing absolutely nothing in this photo. There's definitely 3 of us there being absolutely useless and just there for the photo, trying to look good. But there's also, apart from the preservation, with actual sediments themselves that's influencing this, there's also something at play that's aiding the preservation of that Dinosaurus skull. And this I sort of, at the time, I remember thinking about this because I'd seen it written in the literature about Dinosaurs and more inclusively this group called Anomodonts, which Dinosaurs are a part of. That they have this incredible sort of they have this incredible Karoo record, and it seems largely because their skulls preserve very well. And this is possibly something to do with the the skeletal structure or the sturdiness of the skulls. And it was interesting. It's just some real life evidence and experience that showed that there are certain skeletal elements of different vertebrates that do genuinely just preserve better than others. And that's something I'll pick up a little bit later in the talk. I did also do some unpublished work looking into the completeness of the Temnus model amphibian records. So they're like modern amphibian ancestors. To be honest, very cool. Large predators, occasionally, and there's a large group of interesting amphibians. And I was comparing it to various other groups for of similar completeness studies that had already been done. Now, if you see the purple vial plot there, represents the completeness of Anomodonts, so the Dicynodont thing that we found in South Africa, and the orange vial plot is another unusual Permian and Triassic group of animals called Parareptiles. And those 3, so the green, the orange, and the purple, they all have this like quite contrasting completeness distribution to most of the fossil groups, especially sort of the terrestrial forms. And this, we saw. I mean, this never got published, but it was basically like there must be something to do with their skull preservation, because for some reason these groups, their skull preserves very, very well. But now, if we look at like how dinosaurs match up with other groups, we can see that theropods really have quite low completeness, and compared to other groups, and sauropodomorphs are not too bad. And actually, this is the old data before I did my revisit on sauropodomorphs, but it doesn't really matter. But theropods and sauropodomorphs have like this bottom heavy distribution of completeness scores. So a lot of the species are known from limited material. It's not as bad as the bat fossil record, but it's quite a contrast to things like plesiosaurs and ichthyosaurs, which are Mesozoic marine reptiles, and they're also not dinosaurs, but they commonly get confused by the public. And when we looked at this statistically, we could see that there was that the marine animals were significantly more complete records than the terrestrial ones, and especially the dinosaurs. And this plays into the idea that has generally been sort of knocked about, that the marine record is better and more complete than the terrestrial. And it seems that for Mesozoic reptiles, this is true. It makes a lot of sense. Marine organisms are always sort of submerged in water. They've got a much higher chance of being preserved and fossilized compared to terrestrial organisms, which sort of need to find their way into some, by unfortunate circumstance, into some sort of a river or lake to get fossilized. But yeah. So, going back to South Africa, on our last day in the field in 2017, we actually went to recce a site that Jonah had been given a tip off about. He had been sent some fossil material, and it was from this extremely remote area on the border with Lesotho, near a village of Meha. I think I pronounced that right, probably. And we said. And we were quite sad, the trip was coming to an end, but we weren't, overly optimistic about this visit. We thought it would just be not much there, and it would just be a nice visit and some way to round off the trip. But we got there, really remote, quiet, poor village. The people that were there were living in, basically makeshift huts. And we met with this wonderful guy called Sinyane Raylane, And we went to his home and he showed us his collection of fossils, and one of which was immediately recognizable as being a sauropodomorph dinosaur claw. And all of a sudden we were like, oh, what's going on here? And then we met a couple of other gentlemen, and they showed us some, so they directed us and showed us to the local sites, which were actually, I should say, were actually initially discovered by this guy called Demangwe. And boy, were we wrong to be unoptimistic, because basically on the sites that we saw, there was bone everywhere, like just popping up out of every nook and cranny. And this on the bottom left, you can see is actually a set of articulated vertebrae that's sort of sticking out the rock. There's some huge leg bones in that middle picture just sticking out. And we were really like taken aback, like we couldn't believe what we were seeing, especially considering after like the week we'd had, just like trying desperately to find, get any sort of scrappy bit of material. And so they they showed us lots of different sites, and I mean someone even picked up, so on the top right, someone even picked up this brass badge, which actually is like a cavalry brass horse harness badge from the British Army, and it actually was probably lost during the Boer War, or the Second Boer War in 1899. And so the place was, it was a crazy like 40 minutes to an hour. Just like, oh, what is happening? And you can see like, it was kind of like dawning on us just how exceptional this place was. There's a really nice embrace there with Signane and Jonah, who are realizing how great it is. And if you can see the ginger guy there, that was my supervisor, Richard Butler, and he's looking stupidly giddy in the top left photo. I've never seen him before like that or since. And yeah, it was incredible. So after that sort of euphoria, so we were, there's a picture there, Jonah sort of explaining to these guys that, this is a serious sort of site, and we're going to have to come back to this place, for years to come. It's going to be a huge project. And what, essentially what was there was a bone bed, so it's an incredible find, and almost certainly have dinosaurs and other and things in there. So it could potentially have massive ramifications scientifically, especially considering the potential age of the rocks and the locality. And I know from looking at the record of sauropods and theropod dinosaurs that localities like this, like with that, or places that have bone beds, really provide an opportunity to enhance our knowledge. So on the left, I have separated the completeness scores of sauropodomorphs and theropods by the preservation regime. So like normal standard fossil localities, which is kind of like sort of stuff we were looking at most of the week in that trip, and bone beds, which are also referred to there as concentration Lagerstätte, and also conservation Lagerstätte, which are these localities that have like exceptional preservation. So they have stuff that preserves like entire skeletons and soft tissues. An example of which is Solnhofen limestone in Germany, which produce Archaeopteryx, which you can see on the right of the screen. But there's plenty of others worldwide and within different time periods, and these can be but we see that typically bone beds produce more complete specimens of different species, and conservation Lagerstätte basically just off the charts. They just always produce like amazing finds. So it's really actually interesting how much this impacts our knowledge of actual different groups. So for example, if you can see in the middle picture there, that's basically all the main theropod dinosaur groups that have been split, and their completeness scores is shown. The distribution of the completeness scores is shown for each of them. I'm sure most people have heard of a group called Consignated theropod dinosaurs, and they're these little nasty critters in the Lost World Jurassic Park that that bite the kid at the girl at the start of the film and attack a guy halfway through it. But basically, without like sites of conservation livestock. We basically don't know anything about these. They're almost entirely known from these localities. Now the bone, almost entirely known from this kind. And this has, this has huge sort of macroevolutionary impacts, So again, this is the theropod dinosaur completeness and the species number described through geological time, but split up by the preservation regime. And the patterns at the top are when all the regimes are included, and there's some peaks in the late Jurassic, the mid-early Cretaceous and the end Cretaceous. But those late Jurassic and mid Cretaceous peaks are reduced when we remove bone beds and conservation Lagerstätten. The bone bed at Comeja has the potential to really have a strong impact on the patterns we see in the dinosaur fossil record. And I would expect the impact of the patterns in a positive way, like in a really strong, affect the fossil record in a positive way, but it would change the results that I'm demonstrating here. So a year later, I was invited to go back and start the preliminary digs with a wider team of people at Birmingham and Oxford. Although generally the same place, this was a very different trip because we were staying in Comeja. Some of us in tents and others staying in a local bar, and we were really in like the heart of the community. So it was quite different. It was really eye-opening to see what people like there live like. I was extremely grateful just to have like a bed and a roof, and we were washing out of buckets, and we had to be very conservative with water, but it was incredible. We were there basically just to initially excavate some of those dig sites that we saw and try and establish an age of the sediment that was that these fossils were preserved in, because that was still a little contentious. It was quite important. And we very quickly realized that that big row of vertebrae that I showed earlier was actually a sauropodomorph dinosaur, probably something like Massospondylus or Plateosaurus. It was too big to not be anything else really. And these dinosaurs are basically the earliest sort of sauropods. They're not actually sauropods like the things that you think of, like Diplodocus or Brachiosaurus. But they're like the evolutionary precursors. They're sort of experimenting with quadrupedalism, so that they are actually bipedal by nature, let's say. And they were hugely successful in the late Triassic and the early Jurassic. And when I looked at, I looked at their fossil records, actually really interesting that these early sauropodomorphs have, like the best fossil record of all the sort of major subgroups of sauropodomorpha. And that's actually quite strange in a way, because considering some of the, like, how massive and robust some of the larger sauropod skeletons would have been, and we generally kind of think that things tend to be, have a greater chance of preservation of the fossil record, if they're larger, if they're bigger, they're more robust. But we're essentially seeing the opposite in the sauropod record. And when I looked at this, we argued that this could have been because of certain environmental associations of the larger sauropodomorphs, like the Titanosaurs, and this, and also the sort of fortunate preservation regimes that sort of maybe some of the earlier forms, like the things that we found were found in, but also because we also argued that they're actually quite different. So like the earlier sauropodomorphs and the sort of later large sauropod animals like Titanosaurs were actually extremely different in their body plans, and quite different ecologically. The Titanosaurs had probably, from what we can gather, probably had low population densities in comparison to their ancestors. And so there's less chance of individual skeletons actually sort of finding their way into like a fossilizable scenario, and just the sheer size of some of the big sauropodomorphs, the later sauropods, is that there's actually really long distances between the extremities of their body. So like distal elements actually get lost quickly during decay processes, and like disarticulation was just it becomes easier, and obviously because they're so massive, they're actually prone to scavenging. And that's probably not the case for some of these, these sort of early basal sauropodomorphs, who actually probably had a broad, sort of ecological, the way they lived, they would be more adapted to a wider variety of environments, whereas some of the later sauropods probably actually were quite, had a quite niche sort of ecology and way of living, and that decreases their sort of fossilization. But that's what we argued. But yeah, back to actually the dig, and we spent pretty much all of our days sort of excavating the bone beds, plastering up the rock and getting them prepared for extraction, and it all looks like really fun and games, but what no one really tells you is it's absolutely shattering, and like you're basically just scraping away at rock for like 10 days. It's this, like, even though it's amazing, I completely appreciate where I was and what I was doing, you kind of use this sort of sad realization that if you've come around, come to the southern hemisphere, I've come all the way to South Africa to just like batter away at a rock and like quarry. But it makes it sound bad, but it wasn't that bad. But one of the days I did sort of thought, I need to stop doing this. So there was an opportunity to just go help, with our sort of sedimentology team that were doing like magnetic stratigraphy, and then they were trying to establish like an age date for the beds, and we didn't know what age it was. We didn't know if it was lower Elia or upper Elia, so either late Triassic or early Jurassic, and this is really important because it totally changes the interpretation of the site and how it impacts microevolutionary signals. Like there's a lot of dinosaurs from China and Mongolia where we don't have particularly great like precise age dates for them. So like where they actually fit on sort of the geological timeline is actually still a little bit dubious, and that's really important. That's an important thing to we have to consider when we're looking at some of these large scale signals through time. But what they did establish wasn't me. I mean, I helped a bit, but what they did, the sedimentologists established was that basically the bone bed was late Triassic in age. It was lower Elliott formation, and that's really significant because it potentially gives us an opportunity. It gives us an opportunity to see, into this, like, a time that's we don't have too much stuff. It isn't that, especially for dinosaurs, there isn't that much rich material at this time. And it's going to really advance, I think, sort of our understanding of dinosaur evolution, just from this one bone bed. It's really important. But I mean, that's incredible. And some of the finds were incredible, and and being there and doing the paleontology was really important. But like the biggest and best thing about being there actually was kind of the community we were involved with. They really welcomed us in. I'm vegetarian. They provided me like vegetarian meals and stuff, and I'm probably like the only vegetarian for like 100 miles or something ridiculous. They were wonderful. And it was interesting. We were kind of sort of minor celebrities, in the community. So, we were white, and people in the region, that's quite unusual in that particular locality to see, like, such a group of white people. I remember in one place, like my ex-supervisor's got a big crop of ginger hair, I've got a ginger beard, and people are just like staring at it. It was really interesting. But the locals, they were all extremely interested in what we were doing, and like in most days that we were at the dig site, we had kids wandering down, and even this cool guy on the horse. I mean, how cool can you get? I mean, that was ridiculous. And I had some very interesting conversations with individuals, but it was really great. It was really wonderful to be a part of. In that middle picture, if you can see, I still don't really know what happened with Jonah and that guy. I'm pretty sure he drunkenly bought some of these like fox skins from this guy, but I don't know what happened to them, but I think that's what happened. So there was loads of really interesting interactions, and it was yeah, it was an interesting trip just from a social perspective. There was actually one night. So when we were there, like they were like we had like a campfire, and then there were loads of locals would come round, and most nights they would be like singing songs like collectively, and we're just all sitting there just like, oh man, we're lame Europeans, like not and North Americans, not really doing anything. Like they were doing this sort of amazing sing songs that they were just like, everyone was just picking up. And then one night a colleague of mine actually recommended, like, oh, I think we should do a song, but do a song that we can all do and showcase our sort of culture. And he suggested that we do Always Look on the Bright Side of Life. And so we started singing this song, and honestly, it went down like a lead sinker. Like the people there was like, oh, what are you doing? So we didn't sing after that. It was fun to do that. But we also had, like, there was also politicians that, we had like politicians come down who were interested in the site. I mean, they were interested in taking advantage of it, for their own publicity, but it was really good that they were involved and they knew the significance of the site. I never really had to deal with any sort of that politics stuff, that was for the leaders, but we were all there and we talked to them occasionally. And actually, it was getting really important because on the final day, the South African equivalent of the BBC basically came down and visited the site and filmed stuff for news videos. And I'm now going to show you a clip, just of a newsreel, just because it's just interesting to see what it was like, and it gives you a bit of an insight.
After a fossil discovery in the Eastern Cape, geologists and paleontologists from Wits, Birmingham and Oxford universities have unearthed a number of fossils from different species of dinosaur at Kmeha village near Sturksbrae. Now, the original discovery was made by a wandering villager.
Dinosaurs are creatures of science and a little bit of imagination. But this find and the quality of the fossil deposits sparked huge excitement. The area is referred to as a bone bed or dinosaur graveyard, rare in South Africa. The exploration of this find is in its early stages, but one of the skeletons is believed to be 200 million years old. A 17-meter long tall animal with big head, small arms, and muscle legs.
They're old for dinosaurs, and we don't find old dinosaurs every day. In fact, they're extremely rare. So this site is incredibly significant in that it has these ancient dinosaurs, and that as you look up the riverbed, there's a dinosaur fossil here, there's a skeleton here, there's another skeleton there. So it's very rich too. What we're doing is the start of a long process, and this is going to take at least 10 years, I would say, from the discovery phase all the way up to when we know what species they are, how big they were, what they ate, and that sort of thing.
The man who discovered the find hopes it brings long-term benefits to the future generations of the Kmeha village.
After a fossil...
Yeah, so that last thing that the man was saying was actually like really important, because we were desperate for this to be turning. They were sort of desperate for this to be turned into some sort of conservation attraction and stuff so that they can produce jobs. I'm conscious of time, so I think I'm just going to spin on quite quickly. But I haven't been back since, but there was a trip into 2019 which I went back with an even larger group to excavate some more material. And he hopes to go back most years. I don't know how COVID has affected this. I haven't really heard anything, but I assume they've not been able to go since 2019. But apparently they've, some of the heavy machinery that they've been using has actually helped build infrastructure in the village, and they're trying to like improve the curriculum, the school curriculum now by introducing like geography and stuff. And they've done like community days and things like that that have made more people aware of the site. So hopefully that's a positive thing. This trip to South Africa is also incredible because after the dig, when we went to Johannesburg, and we actually had like a day to kill, and one of the South African paleontologists I was on the trip with, their fiance was actually a researcher at Sterkfontein Caves. now known as like the cradle of humankind. And this place is a place where we've found like human ancestors, like Australopithecus afarensis, like Littlefoot, which is about 3.6 million year old hominid, and also Australopithecus sediva and Homo nallidae. And he actually, he gave us a lovely behind the scenes tour of the caves, which was just insane. And we saw like the excavation sites, and we went to like restricted areas. And the fossil preservation there was really interesting to see, because it's very different to the stuff that we saw at the bone bed and things. And it's in these cases, it gets preserved in a very different way. It's not the rock is actually very soft, and it creates holes at the surface, and basically animals and everything just basically accidentally fall down these holes and then basically die and get buried inside the cave. And this is how it accumulates over time, in like sort of big cones. And it's like the wealth of specimens. There's hundreds of thousands of specimens that you could find, and we were just there, just picking up just like lots of little bone. So it was really amazing to see, and it was amazing for me to see as well, because at the time I just happened to be looking at, I was helping do a paper on the completeness of the bat fossil record, and that's and the bat fossil record is really interesting in other ways, because we know from molecular studies and phylogenetic inference that bats evolved in the Paleocene, and the geological stage that directly follows the Cretaceous. There are no sort of confirmed sort of Paleocene bat fossils, and the earliest bat fossils we have basically seem to have anatomical features we've seen in modern bats. But basically their record is exceptionally poor in an odd way, but also it's poor in its skeletal completeness. It's only not poor when you find bats in like conservation livestock. You find them in like those exceptional deposits that you see. So you only find isolated teeth and jaws and occasional limbs, or like entire bats. And when we did this study, we found that basically the bat fossil record is basically entirely reliant on cave deposits, and then strongly influenced by Largstatten. And this is because they're small, they're delicate, and they have this sort of environment association with caves and also and forests, and then places that are basically not typically preserved in the fossil record. That's probably why we don't have like a pre-bat yet that's found in the Paleocene, because it's thought this evolved in forested environments. But this is also sort of impacts like the dinosaur fossil record, so that the paleo-environment association is also important for dinosaurs. And we saw, for theropods and sauropods, it seems to be that like lake deposit, lacustrine or lake deposits are the most sort of important, and that can get the most sort of complete fossils from, and also sort of aeolian, so like desert environments for theropods. And so you can argue that our actual understanding of dinosaurs is biased again by the fact that it only comes from certain settings. It only predominantly comes from particular settings. So we don't know about the dinosaurs that were potentially living in mountain ranges or in jungles, or potentially living in caves. So there's information there that's lost. I think I'm going to spin on because it's quite. So I'm going to move on. So before now, really, I feel like I'm sort of saying, I'm at a sort of paleo party pooper. I'm sort of slagging off paleontology in a way and pointing at all the things that are wrong with it, wrong with the fossil record. And that was essentially my research goal, was to point out these issues. But nowadays, paleontology really is sort of advancing in incredible ways. And we might think that the golden age of sort of fossil discovery was like in the late 19th century, when paleontology was a bit more Indiana Jonesy, and these two men, Arthur Neil Charles Marsh and Edwin Drinker Cope, were basically fighting each other for fossil discoveries. But if you haven't heard about them, please go and read about them. It's amazing. It's really interesting. But the reality is that nowadays we're actually in a golden age of paleontology. The rate in which new species are being found is just sort of incredible. For dinosaurs alone, it's something like there's a new species like published on like every 2 weeks or something, and I think that might be slightly conservative actually. I'm not too sure, but yeah, there's some bias in that, in the fact that researchers and the public are generally more interested in dinosaurs, so more research gets done because more people are interested in it, and it might be variable for different for non-dinosaur groups. But like the rate is incredible, and here's just a few examples of theropod dinosaur species that have been published in the last few months. There's a lot of finds from South America, as that just seems to be like a relatively untapped paleontological resource. There's a lot of abelosaurid theropods, and there's a new dromaeosaur, a new raptor from Mongolia. And even here in the UK, recently 2 new spinosaurid species were named from the Isle of Wight. And we've now got 3 spinosaurs come from the UK. And yeah, so I mean, they're closely related to Spinosaurus itself, but they would have looked quite different. But all these incredible discoveries are wonderful. They're also quite scary in a way, because especially for someone like myself, who is a data-driven paleontologist, you get all your data together, you finish your data set, and it's all ready for your analysis, and then 2 weeks later, it's out of date. So it's pretty much why I looked at the completeness of the sauropod from a fossil record, which had already been previously done in 2010. We were revisiting it in order to understand those changes that had occurred in those 10 years, and because the number of sauropod species had increased by like a whopping 60% since that initial paper in just like 10 years. So here on the right, there are plots of depicting the number of discoveries through historic time, and with the average completeness in black, and that's per 10-year time beams. And that is split per major sauropod taxonomic group and per continent. And if you look at the grey lines, what you can see is that all the discoveries have all vastly increased in the last 20 years, but have actually sort of skyrocketed in particular groups in the Titanosaurs and the Macronarians, and in South America and Asia. And essentially, this is changing the framework of what we see in macroevolutionary patterns. We can see it's changing the species number. We can see that change in the species number and average scale of completeness through geological time is quite different depending on the decade that you were in looking at it. And it's the most striking change between 2009 and 2019. We actually found that these changes weren't actually really influenced by like fieldwork based discoveries. It was more like taxonomic and stratigraphic age revisions, so like paleontologists doing research like in labs and things. So like and paleontologists like reassessing old skeletal material. That was what was in effect affecting these changes and changing our understanding of patterns through time. So as well as finds and revisions, there's also like many new methods being employed in paleontology that's really enhancing our field and helping us elucidate some of the these evolutionary patterns. I mean, for example, I use something called the Paleobiology Database a lot, and this is basically just a huge free online database that is full of accurate paleontological data, locality information, taxonomic information, all this stuff. I mean, anyone can access it. It has gaps, it has some rich data, but it's constantly being added to, and it's a fantastic resource. But also, nowadays technology is really coming to the forefront of the field. Using computers and high-end software we can recreate skeletons. You can undeform bones on the computer. We can duplicate them and reconstruct animals in more accurate ways. We can CT skull bones and recreate soft tissue of ancient animals in those ways. And we can do crazy things like try and understand like the evolution of soft tissue. So in this example, you can see the changes in the inner ear, the evolution of inner archosaurs. And some of these brilliant things are actually being done on our doorstep. It's being done at the University of Birmingham. I think I'm fairly sure you've previously been given a talk by Dr. Stefan Lundstrager about his work, and he's into all this sort of stuff. And I was lucky actually to help him on a paper where we looked at saber-toothed animals, and there's actually been multiple groups of animals that have convergently evolved saber teeth. not just like the big cats and the famous Smilodon. But we were using methods like biomechanics, morphometric analysis, analysis for looking at evolutionary trends, and we found that like different lineages are actually using saber teeth for a multitude of different ways, not just like using it for one particular killing method. So that was really good study to be involved in. So, to conclude, there are a lot of barriers and bias in the fossil record. There's variable geographical distribution of geological formations, variable preservation of localities and geological formations, variable preservation between different fossil groups, historic and present sampling is different. The sampling methods and efforts are variable, and stratigraphic age dating is really important. I didn't go into museum practice, but I thought I can talk about that later if needed. And like individual interpretation is important, but also I think the one thing that I hope you've taken from this talk, at least, is that that people are important to this, and the key ingredient to a lot of those steps as the people are involved. So I just wanted to sort of slightly finish off and say that I was lucky enough to work with a fantastic group of people during my PhD who were very supportive and very fun people to be around. So yeah, I'll end there. Not too late, only 5 minutes over.
Not at all. Considering the amount of coverage of subject matter you did there, Dan, I think that's amazing. You crammed it all into the hour, so well done for that. So, Dan, if I may, thank you very much again for a wonderful insight. And the one thing I would say is that you've made it very clear to us that going forward, we will better understand what we don't understand.
Yeah. Thank you, Graham. Thank you for having me.
And the final thing for me to say for the evening is to wish everyone here and those members who might watch this via the YouTube channel later a very happy Christmas and a great festive season, and a better, hopefully a more open and free and happy new year. So thank you all, take care, stay safe, and we'll see you in the new year for all the new adventures of the Black Country Geological Society. So from all of us here, thanks again for the year, and bye for now.